So thank you for the kind introduction. So in the next 15 minutes, we will talk about ammonia detection and ammonia sensors. But what do we need to monitor ammonia? Actually, for different purposes. Firstly, for environmental and health purpose, given the fact that ammonia are a precursor of aerosol and they present a high toxicity. Secondly, for industrial purpose, for example, in microelectronics fabrics, pure ppb of ammonia molecules can really decrease drastically the yield of production. Thirdly, for biomedical application, ammonia can be a biomarker of kidney failures, and we can find this biomarker directly in breast. And according to each application, you will find different need in terms of performances for the sensors. So depending on the application, you will look for maybe a long lifespan or for a low limit of detection or even for high selectivity. Commercially, we can find some ammonia sensors as electrochemical sensors or metal oxide sensors. But as you can see here, this commercial sensor cannot match with the requirement from applications. Another alternative is using conductive polymers. But still, we haven't any commercial sensor based on conductive polymers because we still need to work on the stability, the selectivity, and the limit of detection. How does it work? Conductive polymer used for gas sensing. Here we will use some polyaniline, which is doped, so it's a conductive polymers. But when ammonia arrives in contact with these polymers, it will dedopt the polymer, so it turns less conductive. And this reaction is reversible. Basically, in this work, we will work with polyaniline doped with compound sulfonic acid. We disperse it in dichloroacetic acids, and then we had some polyurethane. To have more detail about what we choose this, we can go for our previous work or ask question at the end. Because today, our focus is not on the material, but on how we deposited the material to make the device. So basically, what we are doing, it's cleaning a substrate, which is an interdigitate electrode. We clean with isopropanol, and we deposit 1 microliter of the solution by drop casting. We evaporate the solvent first, and we store it in an oven during a few days. And we obtain these beautiful devices. But then we try to, before drop casting the solution, we try plasma, O2 plasma, as a pretreatment in order to change the wettability of the substrates. And we obtain new samples. And finally, we try to directly print 2 layers of this material using automatic dispenser based on capillary reaction and pressure applied in the syringe. And the idea of this study was to see how this different processing can change the performances of the sensors. To study the performances of the sensors, we have hermetic chamber, shown here, and we can control the humidity, the ammonia concentration, and at the exit of the chamber, we systematically measure the concentration of ammonia and humidity, which is effectively in the chamber. And in the same time, we will follow the resistance measurement of the 20 sensors in the same time. So, the first experiment we have done is to study the influence of humidity on the device. Because normally when we are using this type of devices, we go outside or we are in an environment where the humidity can change. And humidity is known to change the property of the materials. So basically what we do is that we inject little by little an increase of ammonia between 0 and 200 ppb. And we do this experiment at different humidity, 52, 22, and 76% of humidity. Here you can see that independently of the processing, we observe the same trend where the resistance is increasing with ammonia concentration. We have a good sensor, they are working. Great. Then we can also see that here we have nice reversibility, so the response go back to the initial response, and we have a high repeatability. I cannot show you here. You have to believe me that I have the result in another slide. So then, before regarding the response, we have also to focus on the resistance of the sensors and how this resistance before injection of ammonia will change with humidity. And here we see that for drop cast films, the resistance will decrease more with humidity when the humidity increases than with printed sensors. So here we have a decrease of around 11%, when with printed sensor we have a decrease of 3.8%. So here we see that using printing, we can decrease the influence of humidity directly on the change of the resistance, which is a good point for application point of view. Then, once we have this, we will focus on the sensing property. So to do so, we will not focus on the resistance by itself, but on the relative response, which corresponds to the resistance minus the resistance measured just before the injection and divided by the same resistance. Based on this curve, we have the calibration curve here, where we represent the relative response of the sensors as a function of the concentration of ammonia directly measured by a reference analyzer. And then we calculate the slope of this calibration curve in order to have the sensitivity. And it's what we compare in order to see how the processing will impact the performances of the sensors. First, we will focus only on drop cast film. And here we see that independently of the humidity, the drop cast film deposit after plasma treatment is always more sensitive. The sensitivity is multiplied by 1.4 to 3 compared to the traditional isopropanol cleaning. This is, we are supposing that is mainly due to the difference of thicknesses, because we have seen then after that the roughness is not so different. Then we observe that independently of the treatment, we have an increase of the response with the humidity. So this pretreatment will not change how the humidity influences the response. Now, when we focus on the printed samples, we see that the sensitivity is not so impacted by humidity, which can be really interesting for applications. And then, so here, to control if it was coming from the roughness or coming from the thickness, we have measured the roughness of the different samples. But as I said, the roughness cannot explain plainly the difference we are observing. So our hypothesis is that the thickness is even more important, but this needs more investigation to be proved. Now, the last metrologic parameter we are looking for is the limit of detection, meaning that is the lower concentration we are able to measure to discriminate from the noise. So here we see that for the drop cast film, independently of the pretreatment, we are really good limit of detection, lower than 2 ppb. And this is not depending of the humidity. Then when we see here, we look for the limit of detection of printed sensors, this increase a little bit and go up to 4 ppb at higher percentage of humidity. And this is directly due to we have a thinner film, but the resistance is much higher and less stable. So when the humidity is coming, the resistance is less and less stable. So the noise is bigger, and then the limit of detection is higher also. So to conclude, here we have seen that, well, careful when you are cleaning your substrates, because it can change drastically the response of your sensors. It can even increase the sensitivity, depending on which treatment you are using. For the next step, on this point, we want to understand better the origin of these enhancements. Secondly, the printing appears as a promising alternative than manual drop casting, of course. And we have seen that what is important is that it's decreased the influence of humidity. meaning that it increases selectivity of the sensors and make it more available, more useful for applications. To go on this way, we need to optimize the printing of the sensors, given the fact that we have to find the right balance between thin layers, but stability of the resistance, to have the higher sensitivity, but the lower limit of detection. And then the idea is to evaluate the selectivity of these sensors according to different gases. We have already done for drop cast films. It's not responding to acetone, to hydrogen sulfide. It's responding a little bit to NO2, but and then we have to also study the long-term stability. So we have an undergoing study during 1.5 years now, and they are still working. But well, we need to go more. And finally, the idea is to integrate this type of sensors directly in a wearable device in order to make some field campaign. So field campaign for outdoor application, indoor application, but also for outdoor applications. So I would like to thank my colleagues like Edilene Silva, Maria Braunger, who work on this project, and Nathalie Redon, my colleague. This work is supported by the French government and also the company Group Terra, with we are working strongly on this project. And finally, if you want to join our team, we are opening a new postdoc position in 14 months. Thank you.